Welcome back to our lecture series on the material science and metallurgy subject. In today's topic, we will discuss strengthening mechanisms in solids. These are mainly useful for enhancing the mechanical properties through microstructural engineering. So let us discuss about this particular topic in today's lecture. So before going ahead, let us look at our overview of today's lecture content. First, we will see the basic introduction to the strengthening mechanisms. What do you mean by it? And why is it necessary? Why the strengthening is necessary in materials? Then what are the major strengthening mechanisms? Before that, we will let us understand briefly about deformation. Then we will look at what are the major strengthening mechanisms that are present. Then towards the end, we will look at the comparison of strengthening mechanisms and the summary towards the end of the lecture. So strengthening mechanisms prevents dislocation motion, increasing a material's resistance to deformation. So we will look at it, how the dislocation motion will take place in the metals, and how does it increase the material's resistance. We will look at it. So basically, strengthening mechanisms, we are applying certain mechanism to prevent the dislocation motion so that the material's resistance against the deformation that will be increased. In turn, the material property can be enhanced. So what it does by applying the strengthening mechanisms, basically these are used to enhance the strength, toughness and wear resistance of the materials. These are certain properties are directly affected by the strengthening mechanisms. These are essential in industries like automotive industries, aerospace, construction and medical implant industries. We will look at what are the applications in these particular domains towards the end. So why does this strengthening is necessary? So we all know that pure metals are too soft and that are not suitable for most of the engineering applications. And so we have to increase the strength of that material. We have to strengthen those materials. So strength is critical in most of the structural materials and its tools and their mechanical components. Strength is a key component here. So increasing the strength is a key criterion here in the metals. So we apply strengthening mechanisms which basically modifies the material's microstructure in order to increase the resistance against this plastic deformation. So why does the strengthening is necessary? Basically, pure metals will be considered as soft in nature and they don't find any engineering application. Most often they are very limited in its engineering applications. And so strengthening is critical for all the metals for engineering applications. So before going ahead, let us understand the deformation. So we all know that materials experience two types of deformations. One is the elastic deformation, other one is plastic deformation. So what do you mean by this elastic deformation? In another simple layman way, we can also say that this is a temporary deformation. It's elastic deformation. It's basically a temporary deformation. So how do you define it? So when a material is subjected to stress that is very much within its elastic limits. So in the strength of material subject, we know what is this elastic limit. So when the material is subjected to an external stress and that is very much within the elastic limits, it deforms. But when the external stress is being released, it returns to its original shape once the force has been removed. So this is the elastic deformation. It's a temporary deformation caused due to the external stress. Once the stress has been removed, then the material will regain its shape. That is an elastic deformation. So in the stress that is being applied, that is very much within the elastic limits. The classic case study of rubber band, if you consider. So rubber band stretches when pulled but regains its shape once it is being released. So when we stretch the rubber band within its elastic limit, basically it stretches, but once this external force has been removed, the rubber band will regain its original shape. right? So why does it regain its shape? So it is because of the atomic bonds that are closely associated. The atomic bonds stretch, but they do not break here. So if these atomic bonds between the atoms are being broken, and that cannot be considered as an elastic deformation. That is another case, that is a plastic deformation. It's also considered as a permanent deformation, where the atomic bonds will be broken so that it cannot combine and again go back to its initial positions. Atoms will go back to its initial. That will not happen because the stress that is being applied, that is very much sufficient to break the bonds in the case of plastic deformation. In the case of elastic deformation, these atomic bonds are not breaking, and so that allows the material to recover fully. When we consider this plastic deformation is also considered as a permanent deformation, where the applied stress will be exceeds the elastic limits, and so material will undergo a permanent deformation. Its shape will be deformed. So meaning it will not return to its original shape after the stress or the force that has been removed from the material. So it permanently creates a certain deformation within the material, right? That is considered as a plastic deformation. So same case, if you look at the rubber band, when it is been overstretched, when the more amount of force has been applied on the rubber band, so it is overstretched, then what happens? It breaks, and that is becomes it's a permanent reshape, permanent deformation for the rubber band. So what are the two properties? What are the properties which are directly affected by these? One is the strength, other one is the hardness. So these are the properties indicates the material's resistance to the plastic deformation. These are the two two material properties which are basically indicates the material's resistance against the plastic deformation. So if plastic deformation is being arrested in the material, means its material is offering more resistance against this plastic deformation. Indirectly, in turn we call it as a material is having higher strength or the hardness. They are the direct indicators of material's resistance against the plastic deformation. So if you look at this plastic deformation, the microscopic way, that what we have seen at the macroscopic level, with the naked eye, what we can able to see this permanent deformation. But if you look at the microscopic way, at the atomic level particularly, so plastic deformation occurs due to the movement of large number of atoms. When the material is permanently deforming, means certain large number of atoms are being permanently relocated from its initial position. Thereby it's breaking the bonds initially what they are having, and they are being relocated to the new position. So that is what atomically plastic deformation is happening. This process requires this movement of this large number of atoms. When does it happens? When the bonds are being broken, when the rupture and reformation is happen. Rupture means breaking. Here you can consider the breaking of these interatomic bonds, and reforming. It's a move to the new positions. So it's a reforming the shape of the material. So because of this, the plastic deformation can be evident at the macroscopic level, what we see at the naked eye. So in crystalline solids, these plastic deformation primarily happens through the dislocation motion. In the crystalline solids, this plastic deformation primarily is caused due to the dislocation motion. We have seen what is a dislocation in the previous lectures. So the movement of this dislocation causes the plastic deformation of the material. So dislocations, if you recall, these are the defects in the crystal structure that enables the deformation when stress has been applied on the material. So we have seen the two dislocations. One is the edge dislocation and screw dislocation. If you see the edge dislocation moment, an edge dislocation moves in response to the shear stress applied parallel to its line. So edge dislocation will be moving. If you have, what is a edge dislocation? You have group of atoms here, and an extra plane of atom is been considered. So that is considered to be dislocation, edge dislocation. This extra plane of atom is considered to be, there is no plane of atoms here. This extra plane of atom is considered to be the edge dislocation, right? So the moment of this edge dislocation will be when the shear stress is been applied on the material. So this dislocation will move forward in this direction. So parallel to its line, the dislocation will move. So this dislocation moment, edge dislocation moment, it is very much similar to the practical scenario. So it is very much similar to the analogy of caterpillar movement. So how the caterpillar moves. How does it move? It basically lifts the back and pushes forward. So it lifts and then pushes forward so that it moves forward direction. So similarly here also the plane will be shifting from one slipping from, this phenomenon is called in this moment of this dislocation, this phenomenon is called as a slipping between the layers in the materials. Okay, so the ability of a metal to plastically deform, that basically depends on the how easily the dislocation moves. So if the dislocation moment is very easy, then plastic deformation is very much easy for the material. So the ability of metal to undergo plastic deformation is purely depends on how easily the the dislocations are being moved in the material. So indirectly, if you look at reciprocally, if the dislocation moment is being arrested, if you hinder the dislocation moment, then the materials can become, the moment of dislocation has been arrested. So the plastic deformation cannot be allowed within the material. So that means indirectly the material is offering more resistance against the plastic deformation, and that is considered to be material is stronger and harder in its nature, right? So what are the mechanisms? So now we know if we can arrest the moment of dislocations, then material will be offering the more resistance against the plastic deformation. That is indirectly called as a strong material is stronger and harder. So what is the mechanism that we can able to perform so that the materials will become harder and stronger? So these are the 5 major mechanisms that are being considered. So first one is a grain boundary strengthening. That's also called as a Hall pitch effect. Then we have solid solution strengthening method. Then we have work hardening, or also called as a strain hardening technique. Then precipitation hardening. So these precipitations are being formed in the material called as aging heat treatment process. It's also called as age hardening. And finally, we have the dispersion strengthening strategy. So these are the mechanisms through which we will try to arrest the moment of dislocation, so that the plastic deformation can be arrested significantly. Indirectly, you are improving the property of the material. So first we will look at what is grain boundary strengthening. What happens here? What is the concept? So how do we increase it? So we have to strengthen the grain boundaries. That means indirectly we are doing it. We are increasing the grain boundaries in the material. So how you can able to increase the grain boundaries? So that the dislocation will travel. So something like this. This is the extra plane of atoms, let us say. So let us say this is the boundary, and this is another atom again, another grain, let us say. Okay. and we consider this is another boundary. So we have to, this as dislocation is moving, it moves forward and reaches to the boundary region. At this boundary region, we will not be having, atoms are not being aligned to either grain A or grain B, and so the entire moment of this dislocation will be arrested at the grain boundaries. If we can increase such grain boundaries, then we can able to arrest this dislocation moment. So how do we increase the grain boundaries? So what we have to do is, if we make smaller and smaller grains, if we divide and smaller grains, you will be basically creating more and more boundaries. Okay. So more and more boundaries are there, so that all the dislocations, the moment of dislocation can reach to the boundary region and that can be arrested significantly. So the concept of this grain boundary strengthening is, we have to reduce the grain size. Okay, we have to bring in the smaller grains so that more grain boundaries can be formed. So these grain boundaries will hinder the moment of dislocation motion, and that is how it strengthens the material. Why? Grain boundaries acts as a barriers for the dislocation moment. So what is a Hall-Page equation? Hall-Page equation is sigma y, that is yield strength, that is equal to sigma naught, that is a materials constant, plus ky is a strengthening coefficient, multiplied by 1 by root d. 1 by root d to the power of minus 1 by 2 is nothing but 1 by root d. So it is indirectly proportional. The yield strength is indirectly proportional to the grain size, the grain diameter. So if the grain diameter is reduced, so this yield strength will be increased. That is a relation between. So sigma y is indirectly proportional to grain diameter. So grain diameter, if it is reduced, then strength can be improved. That is a concept here. So fine grained steel, example, fine grained steel can be stronger than the coarse grained steel. If the same steel, which is having coarse grains, that is a bigger grains, and which is having finer grains, so finer grained steel will be stronger than the coarse grained steels. Then comes to the next mechanism, that is a solid solution strengthening. So what do we do here? So here we will be adding the alloying elements. We will be adding the alloying elements that distorts the entire lattice and impedes the movement, impedes the dislocation moment. So when we are adding foreign atoms or alloying elements into the crystal lattice, what happens is these alloying elements will be having smaller, or either it could be smaller or bigger atomic sizes. And so it disturbs the entire lattice structure, and the moment of dislocation can be arrested here. So these impurities interact with the dislocations, and it's basically, if not arresting, it slows down. Its moment of dislocation can be significantly slowed down. So example could be, if we take the brass is a combination of copper and zinc. So zinc atoms strengthens the copper by introducing the lattice strain in the material. So it causes the lattice strain because of the presence of zinc atoms in the copper. Then we have the stainless steel. Stainless steel, obviously, it is iron and chromium. Carbon will be there, and chromium and nickel is also there. Chromium and nickel is a alloying elements along with the carbon. Chromium and nickel will enhance the corrosion resistance and strength here. So where are the industrial uses? These can be used in the turbine blades, and structural alloys can be produced. Strengthened structural alloys can be used in different industrial applications. So by adding the impure atoms in the structure, in the lattice structure, you can distort the overall lattice and induces certain lattice strains that will significantly slows down the motion of dislocations. That is how we can improve the material strength. Then we have work hardening or strain hardening. So it is we will be introducing the plastic deformation into the material. We will allow the plastic deformation to certain level, so that it will be increasing the dislocation density. So dislocations will be reached to a particular region, and they will be closely present one to other, and they will be indirectly the further any dislocation movements will be significantly arrested. That's also one of the strategy. So dislocations will interact and block each other. They are close to each other, and they will be blocking one another, and which will significantly reduces the further motion of the dislocation, so that the material can be strengthened. So we will be straining the material up to this particular range. After that particular point, the further deformation is difficult, and so we can consider the material is attained significant strength. The process is something similar to the cold working operations that we perform, like rolling, drawing, and forging techniques that have been introduced to strain harden the material. Examples could be our cold rolled steel is stronger than rolled steel is stronger than the stronger, but which is less ductile in its nature, and the copper, which is drawn pure copper is soft in nature. So the copper wires that have been drawn through this method, they will be having significant strength because of this plastic deformation that we are introducing into the material through the drawing process. Then the next technique is the precipitation hardening, or it's also called as age hardening technique. So the concept is here, the small precipitate particles will block the dislocation motion. So we will be purposefully introducing the precipitates into the lattice, crystal lattice, and which will be blocking the dislocation motion. So what are the steps that we follow to introduce the precipitation is, first we will solutionize the material through heat treatment process. We dissolve the alloying elements. Then we quench it, which is nothing but rapid cooling of the material to create a super saturated solid solution. And after that, we apply an aging heat treatment process, which is called as a controlled reheating of the material to form a fine precipitates. So these is the steps that we follow for generating or introducing the precipitates into the material. So what are the materials that we use? 7075 aluminum alloy, that is a combination of aluminum, zinc, magnesium, and copper, which is used in aircraft structures. Basically, will be having the precipitate. Then maraging steels that are used in aerospace and military applications, that is also an example of hardened material, precipitation hardened material. Then we have dispersion strengthening technique. So here we will be dispersing the second phase particles like carbides and oxides to strengthen the material. What happens is particles will undergo the dislocation. These particles will hinder the dislocation motion and improves the high temperature performance, because these are the carbides and oxides are the ceramic in nature, and so the high temperature withstanding abilities of the material can be significantly improved. And also it hinders the dislocation motion. Both the strength and also the high temperature performance of the material can be improved through this dispersion strengthening techniques. What are the examples? ODS alloys, like oxide dispersed strengthening alloys, which are used in jet engines and nuclear reactors. That is a classic example. Then carbide strengthening steels also will be used for enhancing the wear resistance of the material. So if you look at the comparison of the strengthening mechanisms, so first case, the key feature what we discussed is grain boundaries. The smaller the grains, the higher the strength. So grain boundaries will be enhanced, so higher the strength. And example is a fine grain strain. Then the solid solution strengthening, alloying elements impedes the dislocation. So alloying elements are being introduced into the material, which impedes the dislocation motion. That is, examples could be brass and stainless steel. Work hardening is cold working operations like drawing, rolling operations we perform, so that increases the dislocation density. And so it will be arresting the further motion of the dislocations. Cold rolled steels and copper wires are the classic examples. And precipitation hardening, we will be introducing the fine precipitates into the material to block the dislocations, like maraging steels and aluminum 7075. Dispersion strengthening. So certain particles are being introduced through dispersion method, and which these particles will arrest the material dislocation motion and also improve the high temperature performances. Jet engine components can be, as we have discussed already in case by case example. So we have applications in automotive segment, aerospace, medical implants and construction here. Then in the case of medical implant, you can see the grained refined titanium alloys can be used for biocompatible applications, right? Then in the construction, we have the strain hardened rebars also we are using in the composite applications for earthquake resistant structures. If we summarize, strengthening mechanisms improves material properties by resisting the dislocation motion. The key concept is you have to hinder the motion of the dislocation. So in the case of grain boundary strengthening, smaller grains creates a stronger material. Solid solution strengthening, allowing elements hinders the dislocation. Work hardening technique, cold working processes increases the dislocation densities. And precipitation hardening, heat treatment process reforms introduces the precipitate into the material that strengthen the particles. And the dispersion strengthening, hard second phase materials like oxides and carbides are being improved for its high temperature performance of the materials. So I have referred this Callister textbook for making the PPT, as well as the OpenAI tools for developing the content for the lecture series. I'll be thankful for both of these. So thank you for today's lecture, and in the next class we will talk about the Unit 2 contents. Thank you.